I'm so overwhelmed.
Well, we're getting close. We're getting close. We're going to finish this up, and then I want to show you guys slope fields, but slope fields it's like nothing. It just takes a second. And then we're kind of to the end. Okay, so we were working on this one, right? Finding the general solution of the separable first order differential equation. Okay, so what's the point here? The point is we can separate all the variables, the y's to the side with the dy, and the x's to the side with the dx, right? And then how do we undo this? How are we going to turn this into a solution of this differential equation? Because what we've done is we've taken the differential equation and we've just written it in differential form where I've got the dy on one side and the dx on the other side. But what would I do? How do we undo differential equations? Integral. Yeah, we just integrate both sides, right? So if I integrate both sides, we'll just see what we get. So on the left side, that's the same thing as y to the negative 2 dy, right? What's the integral of y to the negative 2 dy? Because isn't that just y to the negative 2?
Yeah.
Right?
So true. So y to the negative 1 over negative 1.
Okay, which just means negative y to the negative 1. Okay, so then that is just negative 1 over y. And we get a constant, but we'll lump the constants all together on one side. Okay, now what? How about the other side? What's the integral of 3x dx? 3/2 x squared plus some constant, right? Good. And then we'll lump all the constants together in that one constant, and there's our solution. Okay, there's our solution. That's the solution that tells us, what y is, how y and x are related in the original equation. We could solve that for y if we wanted to. I mean, it would be, we don't really have to, but we could if I wanted to multiply each side by -1. Say we call that C1. If I multiply each side by -1, I would just get 1 over y equals, we'll call it C instead of C1, C minus 3/2 x squared. And then I could just flip each side and get y equals 1 over C minus 3/2 x squared. If I really wanted to solve for y, that's the function that we could differentiate to get this differential equation. Okay? But we could even just leave it like that. That's easier. Okay, easier way to look at it. So it says find the particular solution with the initial condition y equals 2 if x equals 1. What would we do? Substitute and solve for c, right? So if we did that, we would then just get -1/2 equals 3/2 plus c, if we just call that, or c1, whatever we called it. Subtract 3/2, and I would just get c equals -2. So I would just plug that back into the equation, and we'd get -1 over y equals 3/2 x squared minus 2. There's the particular solution that corresponds to that initial condition. Okay? No big deal, right? That's how we solve a separable differential equation. We separate the variables and integrate. Okay, so let's look at a particularly important class of separable differential equations. These are growth and decay functions. This is a big deal, right? In the natural world, or in the financial world, things grow and decay all the time, right? And this is a pretty interesting model for that. So there are situations in science, nature, and economics, such as radioactive decay, for example, population growth, interest, investment growth, right? Investments grow as they earn interest, in which a quantity A varies with time in such a way, this is really important. Here's the part you got to really focus on. A varies with time in such a way that the rate of change of A with respect to T is proportional to A itself. Now, doesn't that make sense? If you want to look at population growth, for example, say we're looking at lemmings in Norway, okay? The population of lemmings in Norway, you know what lemmings are? They're little rodents. So
I thought Lemmings was a town. Like Lemmings.
No. It's just they're little animals. So if we look at the population of lemmings in Norway, tell me why it would have to be true that the rate of change of the population of lemmings would have to be proportional to the population size. Yeah. How do lemmings reproduce? Well, lemmings reproduce lemmings, right? So the rate of change of the population would have to be based on the number of lemmings that you're starting with, right? If I have 400 lemmings, population is going to increase a lot faster than if I had 5 lemmings, right? Because there's more lemmings to reproduce. Okay? So, or bacteria, right? If you look at the growth of a sample of bacteria, the rate of change of the number of bacteria is going to depend on the amount that you have at that given time, right? So this is a really natural thing that we can just intuit. There are many situations in the universe where the rate of change of a quantity is proportional to the size of the quantity. Okay, so this seems like a pretty interesting and example to look at. And I'm going to go to maybe this page. Okay, when the rate of change of a quantity A is proportional to A, this leads to exponential growth or decay. Okay, so first of all, what does that mean? The rate of change of A is proportional to A. One way to say that is like this. This is a proportionality symbol. This says the rate of change of A with respect to T is proportional to A. That's not very useful because you can't do algebra with a proportionality symbol. You can only do algebra with, and well, you can do other things too, but we'd like an equation. So instead, we can trade that for this proportionality. We can trade for this equation, dA dt equals K times A, where K is some constant. We call it the constant of proportionality, right? So what if the constant of proportionality, how is this different? Like if the constant of proportionality is 4 instead of 2, what does that tell us? If the rate of change, if dA dt equals 4A compared to 2A, what does that tell us?
It's double.
Faster, yeah, right? Tells us that the rate is twice as fast if K is 4, okay? Where K is the constant of proportionality, but they're both proportionalities. Okay, give me 1 to 5 so far. You guys remember about proportionalities, right? If all that means, proportionality means, is if I have an equation like this, regardless of what K is, if A doubles, then dA dt would double also, right? Agreed? Okay. Okay, so, oops. Is this one? Yeah, okay, so this is a separable differential equation, so we solve by separating the variables. What are my variables in that differential equation?
A and T.
A and T, exactly. So we want to get the A's on the side with the dA and the T's on the side where the dt is on top, which would be the right side. So I'll multiply each side by dt, and I get that, right? I get the dt over here, and then I would divide each side by A to get the A over on the left side with the dA. I separated the variables, right? Everybody see that? Isn't that cool? Now we can solve this by integrating. So we'll take the integral of dA over A on the left side, the integral of K dt on the right side. This is a really easy one to solve. What's the integral of dA over A?
L and A.
Yeah, natural log of A, right? It's the natural log of the absolute value of A, but A is always positive, right? A is a population, so it can't be negative. So we end up with natural log A on the left side. And the right side, what's the integral of K dt? K is a constant. KT. Plus some constant, call it C1. Okay? So there's the solution, but we want to try to maybe make this a little more meaningful. So one thing we'd like to do is we'd like to be able to come up with a function a of t where we can predict the population size. So we don't really want the a to be absorbed inside this log function. Yeah, we want to exponentiate both sides to free the a from the log function. So we can do that. If we exponentiate both sides, e to the log a is a. And on the other side, we get e to the kt plus c1. Okay, well, what can we do with that? Well, we get the a where we want it by itself. We can use a property of exponents here, right? We know that a to the m prime n, same thing as a to the m, sorry, get that backwards. A to the m times a to the n equals a to the what? M plus n. Well, we can go both ways with that. We could also start here and go that way. I could split this up, e to the kt plus c1, I could split into the product of e to the kt times e to the c1, right? Everybody agree? Good so far? E to the c1, that's a constant to a constant. E is a constant, right? So e to the c1, I'll just call that some other constant, right? Call it c. So I get something like that. Okay, like that. So I've got two constants in my answer, c and k. Let's try to come up with the meaning of these. Anybody want to predict what the meaning of c is?
Is it like the base number of things you start with?
It is. It's the initial value, and we can show that pretty easily. What if we just let t equal 0? Right? If I let t equal 0, a of 0, a at times 0, would be c times e to the k times 0, or e to the 0. E to the 0 is 1. So we just showed that c is equal to the population size, or the amount. It may not be a population. The amount of our sample at times 0. Okay, so we'll just call that a naught, or a sub 0. Anytime you say naught in math, it just means sub 0. Okay, so that's the initial value of a. And we end up with, I guess I can get rid of this now. And we end up with that, right? So we end up with this new model. A of t equals a naught times e to the kt, where k represents, k is the growth constant. The growth or decay constant is what we call that. If k is positive, it's a growth constant. That's exponential growth. If k is negative, it's decay. The amount is going to be decreasing with time, and that's exponential decay. Okay, makes sense? That's huge because many, many, many things follow this model. Now, let me back up just a little bit. This is uninhibited growth and decay, right? This is if the growth it's explosive and it never stops, or the decay is never going to stop. So what does that look like? Well, it looks like that. That's exponential growth. There's the initial population size. Let's say if we're talking about a population, and it's going up exponentially. Okay, this is exponential decay. There's the initial amount, and it's decaying towards 0. Does it ever get to 0? According to this model, no, never gets there, but it approaches 0. Do you see a problem with this on planet Earth, for example? With uninhibited exponential growth.
Then the lemmings would rule the earth.
Yeah, the lemmings would rule the earth, exactly. They would be our overlords, and they would control things. Okay, but things like that don't actually happen. Lemming populations in Norway do explode periodically. I think it's like every 7 years or something. The lemmings. You know what they do? The lemmings, as their population explodes, they start to become so stressed that they just start jumping off cliffs and things. It's crazy. Yeah, I'm pretty sure. We'll look it up here at the end. We need to leave a little time. But the lemmings, but you could look at bacteria, for example. Even bacteria. Look at bacteria in a petri dish, and the bacteria grow explosively for a while, but eventually it dies. They can't live forever. How come? Why does anything on Earth eventually it's going to run into a wall here? Well, I mean we'll talk about that, but that's a different story.
They're cute.
Why can the lemmings not keep going forever?
Because the environment can't sustain them.
The environment can't sustain them. Exactly. Right. They.
Oh, it is cute.
That's a lemming. Okay. Yeah. Little furry. I knew what they were.
It's cute. It's like a yellow chipmunk. It's cute.
These. I think they just don't have tails or something though. They're a little bit.
They don't have tails. I would have one as a pet.
Or they're real stubby little tails maybe.
Aw, it's cute.
So yeah, eventually, aside from the fact that the lemmings get stressed, I mean, because as the population increases, their stress level just gets unmanageably high. But they can't. Even if that didn't happen, they couldn't survive because there's not enough resources. The Earth, it has finite resources, even though we sometimes seem to forget that, has finite resources, and so any infinitely growing population is eventually going to run into problems because you can't sustain that. So uninhibited growth rarely ever occurs. Well, biologically, it can't occur. And it doesn't even really occur very often in physics. I mean, at some point, usually things run into scarcity of resources or scarcity of constituent particles or whatever, and it can't be sustained. But it's a good model for a while. Okay, so now let's look at an example. Okay. Here's an example. Assume that a colony of bacteria grows at a rate proportional to the number of bacteria present. So what's that telling us?
The A is proportional to A.
Yeah. So if we're going to call this colony of bacteria, if we call that N is the number of bacteria, isn't that just saying N is proportional to, or sorry, dN dt is proportional to N?
Yes.
Right? We know the solution of that. We just did all that. We don't have to do it every time. What's that work out to be? N of T then is what? What's the,
Oh, it's
what's
C. It's C, right?
N naught? Good. Initial population size times E to the KT. Yeah, we know that these are the conditions for exponential growth, uninhibited exponential growth. And so that's the solution. We've already solved that differential equation. That's what we get. Okay, so then we need to come up with some specifics though, because if we're talking about a specific colony of bacteria, so we need to be able to fill in the unknowns here. What are they? What are the things we've got to put numbers to? If we want to use this as a predictive model, and not, we need to know what that is. What else? Not time is a variable. That's K. Yeah, right. The growth constant. We need to know what the growth constant is because that's going to depend on this specific how this population grows. How quickly does it grow? Right. That's all contained in that K. So how am I going to find those things? Well, I need some information. Okay, it doubles in 5 hours. Yeah. Okay. Okay. How long does it take for the population of the colony to triple? So, do we actually need to know the initial population size to know how long it triples? No, we don't. We just need to know that it's going to grow by a factor of 3, right? Okay, but this must be important. If the population of the colony doubles in 5 hours, how can I use that to solve for K? So what is, in other words, what is, if we're measuring T in hours, what is N of 5 going to equal? 2 times,
N, E, something.
well, okay, but if it doubles from its starting value, right, in 5 hours,
2N?
but you got to be more specific.
2 times the original.
Okay, what do we call the original population?
N naught.
N naught, so it'd be 2N naught,
Oh, that's
right?
okay.
Okay.
Okay, yeah.
2N naught. And we have a model for this, right? If we want to solve for T, well, all we have to do is just solve for T in our original equation up here, right? Or, I mean, not solve for T, solve for K. The value of T is 5. N of 5 Isn't that just n naught times e to the 5k? Because I'm plugging 5 in for t in my function?
Yeah.
Everybody agree? Okay, look at this equation right here. What do you notice about that equation? What can I do right away to make it simpler?
It says no. Wait, do we not have to, why do we just lose that 2?
Why did we lose the 2? Okay, because n of 5, there's two things. Let me write it in two ways. Let's do this. Okay, so here's something we know. The population of the colony doubles. The fact that it doubles gives us that equation, right? It's twice as big as it was originally. Okay, in 5 hours, oops. In 5 hours means we're just plugging 5 in for t, right? So that gives us the equation n of 5 equals n naught e to the k times 5, which is 5k, right? This is what our model tells me. That is the output for n of 5. But they told me that the population doubles in 5 hours, so I know it's equal to 2 times n naught. Okay, that's pretty important because look what happens when I set these two things equal to each other, right? 2 n naught equals n naught e to the 5k. What can I do to make this simpler?
Take the antiderivative.
Well, I don't have to do that yet. Yeah, I can divide each side by n naught, right? Look at that. That's the math gods telling us something really profound. If I can divide away a number like n naught to get it means it's irrelevant. Exactly. It means it's irrelevant. It means that the solution is insensitive to the original population size, is how we'd say that. It doesn't matter, right? It doesn't matter what the original population size was. The amount of time it takes to double is not going to change regardless. Okay, so 2 equals e to the 5k. Now all I have to do is just solve for the only unknown, which is k. How would I solve for k there? Yeah, right. The way I undo a base e exponential is to log both sides. So I'd get log 2 equals equals 5k. So what's k equal to? Yeah. So k just equals log 2 over 5, which is just some calculator number, right? And now that I know what k is, we can plug that back in and we can use that to solve for how long it takes the population of the colony to triple, right? So what that tells us then is that n of t equals n naught e to the kt. So I get e to the log 2 over 5 times t. Right? Everybody get that? So that's my exact model for this population right there. Okay, now let's use it to answer the other question. The question that we're being asked here is, how long does it take? Right there, yeah. How long does it take for the population to triple? Okay, how can I use my model to do that? Here's my model. What am I going to set that equal to if I want to figure out how long it takes the population to triple? 3 n naught. Exactly. And look what happens. Again, yeah, those go away. Doesn't matter what it was. It's just going to triple. Whatever it was, it's going to triple. So now we've got this equation we have to solve. We would log both sides, wouldn't we? Yeah, sure. Sure, because all this stuff is inside the exponential function, right? So logging both sides just undoes the exponential function. Keep in mind, this is just, what is that? That's just some number. We could put it in a calculator. It's just going to give us some crazy decimal. It's just a number. So e to that constant times t equals 3. And so we would just log both sides. Absolutely. Okay, and we end up with log 2 over 5t equals log 3. So what's my solution then? T equals, and wouldn't I just multiply each side by the reciprocal of that fraction? Multiply by 5 over log 2?
Yeah.
Okay, so I'm going to get t equals 5 log 3 over log 2. So what is that? If I plug that in a calculator, roughly. 7.92 hours. How about that? Pretty amazing, huh? We can solve that. Okay, make sense?
Yes.
All right, let's look at another one. So doubling time. This is kind of cool.
Doubling.
Yeah. And I have to admit, when I did this, I kind of, when I wrote this up, there were some things in here. I was like, well, that's not right. I was looking at some of these things, like in our textbook and online, and it's not. There are some things that I want to show you something that people do a lot of times. They make an assumption here that is incorrect. It's a little bit incorrect. It works, and I'll show you why it works in some cases, but you want to be a little bit careful about this. This is kind of cool. I actually really enjoyed this because I learned a little something here that I hadn't really thought about before. So when you want to look at, when you want to gauge exponential growth, it's difficult for us to do because people don't think in terms of exponential growth very often. Very few things that we do in life follow that model, right? Exponential growth is really aggressive growth. And so a lot of times people will not really understand the ramifications of something like, let's say, I don't know, let's just say something like 7% population growth. Does that sound like a big deal? Like if we said, okay, our goal is to make Pendleton, it's a little bit stagnant, the economy, we want 7% population growth. And then we feel like that's going to sustain a growing economy in Pendleton. Does that sound okay?
Sure.
This sounds okay, doesn't it? 7% doesn't sound like very much. But a good thing to do whenever you're given something like that is you always want to use they call it the rule of 72 or the rule of 70. Rule of 70 is really better. You should say the rule of 70, and I'll show you why. 72 is just a more highly divisible number, so people use it all the time because it divides evenly by more things. But I picked 7 on purpose. So if you divide 70 by the annual growth rate, it tells you the doubling time. It approximates the doubling time. So 70 divided by 7 is 10. So if we suggested that 7% growth in Pendleton was a good idea, that means that the population of Pendleton would be doubling every 10 years. Now that might change your opinion, right? 7% sounded okay. That didn't sound like that big a deal. But doubling the population of Pendleton every 10 years, that seems a little bit crazy, right? If we assume our population is 17,000 right now, so you guys go away to college, and maybe you go to graduate school. By the time you come back from graduate school, you do a master's program, you maybe take a maybe, but just to keep it at 7 years, let's just say all you do is you go away to school and you do a master's program, maybe with a little gap in there to make it 7 years. You come back after that, and Pendleton's gone from 17,000 to 34,000. Okay, so you move away for a while and you go to a different part of the country for 7 years, and then you get a job opportunity over here. So you come back, and now Pendleton, which you're used to being little old sleepy Pendleton, 17,000 people, is now 68,000 people.
That would be crazy.
That's crazy. And so, by the time maybe let's say you got a family and your kids are starting school, 7 years later, all of a sudden Pendleton is bigger than Bend is right now. And 7 years after that, by the time your kids are maybe like in middle school, all of a sudden Pendleton is the size of Portland, downtown Portland. So you can see where it doesn't really make sense a lot of times. Like people do that. I listened to this guy. He was at the University of Colorado. I was a big fan of this guy. He was a physicist, and he was a real expert in exponential growth. Like he studied finite resource exploitation. Like, and it's really interesting. This guy I just used to listen to his lectures all the time, and he always made this statement. I'm convinced there's at least a dozen people in this country that understand basic undergraduate calculus. But I'm not so sure because nobody ever really seems to put a check on these statements. Like he's always talking about that. About this guy was kind of a crotchety old guy. He was funny. And he's saying if people really understood this, they wouldn't say crazy things like we're going to grow the U.S. economy at 4%. Well, you can't do that. You can't sustain. It's impossible to do because that would be doubling the size of the U.S. economy. Every 70 divided by 4 years, that's less than 20 years. You're going to double the size of the U.S. economy. That's not practical, right? That just can't happen. And so when politicians say things like this, most of the time they just don't have a clue because they don't understand any of the math behind it. But sometimes, even if they did, they're just trying to get elected, probably. But when people say, whenever you hear people talk about percentage growth like this, you always want to apply the rule of 70 and say, okay, is that good or bad? If I think about it in terms of doubling time, I'll show you how we get 70. So here, let's look at this little proof. So if we say that our percent growth means that after 1 unit of time, say a year, we'll make this annual. After 1 unit of time or 1 year, A will have grown by R percent. It's R percent bigger than it was originally, right? So in other words, A of 1 is going to equal R. If I plug in, A naught times E to the KT, well, that's A naught times E to the K times 1, A naught E to the K. And that would have to equal my original size, A naught, plus that additional amount, R times A naught, right? Where R is the growth rate written as a decimal. Okay, so like if the growth rate were 7%, then after 1 year, we would have the original amount plus 0.07 times the original amount, which is the same thing as 1.07 times the original amount. It's grown by 7%. Okay, so we could, in other words, if we factor out an A naught, we could just write it like that, right? A naught times the quantity 1 plus R, where R is the annual growth rate. Okay, so what's this tell us then? This tells us that E to the K, if I divide each side by A naught, E to the K is equal to 1 plus R. Okay, so here's the part where people mess this up. They always assume that K is the growth rate. It's not. It's not at all. K is, if I solve for K here, K is the log of 1 plus R. It's not the growth rate. But here's why you can sometimes get away with that and not even realize you're doing it. And I have to believe that, like most people that are making these statements probably know this, but they just don't articulate it very well. So if we go down here, right here. So here's what we're saying. K can be approximated by R. So K is approximately equal to the growth rate because of this. I'm sure you're really surprised I cooked up a little Desmos document here. So if here is R, okay, here is this is the growth rate, and here is the natural log of 1 plus R. Well, look, they seem to diverge. They don't seem at all similar unless I go in here and I focus on very small values of R. If I look at small values of R, they're pretty close, aren't they? And how small are these values? Well, they're not that small. Like a growth rate that 0.02 means 2%, right? For a 2% growth rate, R and the natural log of 1 plus R, so K, are very close. If I go up to 4%, they're still pretty close, right? It's not until I get up here above like about 10% that they start to really diverge. And once you get up to something like, 20%, yeah, now we're starting to, that's not working so well. So as long as the growth rate is small, it's a good model. The rule of 70 works well. If you're using big percentage, growth rates, then you got to take it with a grain of salt. It's not going to be that accurate an estimate. Okay, how can we show this though? If we make that assumption for small values of r, that k is roughly equal to r, then look what this does, right? It tells us that a of t, the doubling time, right? A of t equals 2 times the original amount, a naught, 2 times our initial amount, which is equal to a naught times e to the kt, right? So if we divide out the a naughts, right, we can divide that away. We're using the Ashton maneuver of getting rid of those, right, of canceling those out. That's what, henceforth, that's what that'll be is going to be called. And these they're irrelevant, right? There you go. There you go. So we end up with this new equation. 2 equals e to the kt, log both sides, and we get kt equals log 2. But remember, k is approximated by r for small values of r. So we could just say rt equals log 2, right? Okay, so then if RT equals log 2, let me write that down. I didn't put it on here. RT is approximately equal to log 2. So if I solve for t is approximately equal to log 2 over r. Okay, well, r is a percent, right? But it's written as a decimal. So if I want to turn it into a percent, I've got to multiply the top and the bottom each by 100, right? A growth rate of 7% is 0.07. But if I want to write that as 7% on the bottom, I could multiply top and bottom by 100. And what's that give me? 100 times log 2 is about 69 point something, right? So 69 divided, so really 69 is the best number, but 70 is just a one that's a little bit, it's multiple of 10, so we'll use that. And people a lot of times would even up that to 72 because 72 is more highly divisible. But that's how we get that rule of 70. It's pretty easy, right? That's it. So 70 divided by the annual growth rate estimates doubling time. Okay. All right. So let's look at another example here. If $1,200 is invested in an account that earns 2% annual interest compounded continuously. So that means exponential growth. How does that, have you guys ever talked about this? Like if I compounded, yeah, okay, so you guys learned about PERT. So if it's compounded a finite number of times, we use PERT, right? Where like if it's compounded monthly, what would the number of compoundings per year be? 12. Okay, so then that would be 12. If we compounded it weekly, it'd be 52. If we compounded it daily, it would be 365 and a quarter, kind of a thing, right? And so you get, but if we let the number of compoundings approach infinity, then PERT becomes our exponential growth model, right? Then it just becomes a naught e to the kt, right? And that's what we call compounded continuously. And that's usually what financial people would use is interest would be compounded continuously. Easier to calculate with, work with that. So how long will it take to double the original $1,200? I mean, we could estimate with the rule of 70. So by the rule of 70, what does that tell us? If it's a 2% rate, how long would it take to double your money? How many years? 35, right? 70 divided by the growth rate tells you the doubling time. Yeah. Let's actually see what it is. Okay, and we can compare it to the rule of 70. How would we do this? So what's our model here if it's compounded continuously? Yeah. Go ahead. What were you going to say? Okay, right. So we even know the amounts here, don't we? So we know A of t is going to equal our original amount, which is 1,200, right, times e to the kt. Okay, if the interest rate, oh, you know what? Okay. If the interest rate is 12%, so we have to do a little, we don't know what k is yet, do we? Right, we have to find k. So how could I find k here exactly? How much are we going to have? What is a of 1 going to be? Well, if it's a 2% annual interest rate, a of 1 is guaranteed to be something we'll talk about tomorrow.
Good transition.
Yep.